Man has mastered many of the forces of nature. He has learned to harness power and uses it to span continents, to drive machines, to light the world. Yet electrical power can be so finely controlled that a child at play can safely use the converted force of a river many miles away. Or a scientist to operate the most delicate electrical instruments in his laboratory. Thus, control is the measure of man's real victory over the powers of nature. Without it, the modern hydroelectric power plants and the tremendous energy produced by their generators would destroy, not serve, those who would try to use it. Since time began, man has known and feared that mysterious force which we call electricity. From the earliest days, he felt the fury of lightning, a force so swift and violent that it can serve no useful purpose. So man developed his own means of producing electricity and controlling his newfound power. That is the real victory over that great force of nature, electricity. Humming their high-pitched song, the generators whirl under the impact of tons of water on their turbine blades, creating the giant electricity. The giant is a combination of pressure and current, what is commonly known as electric power. The currents produced by the waterfall are carried from the powerhouse to the city at the enormous pressure of hundreds of thousands of volts. The giant can travel over great distances without losing his strength, but he must be given legs and a roadway. The legs are the tall towers which trace their delicate pattern against the sky. The roadway, the high voltage transmission lines which reach out across the countryside. It takes experience and skill and daring to build transmission towers. Sometimes they are built lying on the ground and then raised into their proper position. But usually they are built from the ground up, section by section. When the towers are in position, the linesmen install the heavy lines, insulated by thick porcelain. On a cold day with a high wind blowing, it's no joke to be dangling in midair. Finally, the line goes through. The highways of electric power cannot detour. They strike boldly through the land, following the quick, direct way to the city, whose life-giving arteries they are. Unseen and silent, the electrical energy flows along the transmission lines at the tremendous speed of 186,000 miles per second. At the gates of the city, the electrical giant meets its master, the power substation. Here, the force generated at the powerhouse is broken down into usable units. In Montreal, there are many of these substations, varying in size and type according to the requirements of the area which they serve. The Cartierville substation is typical of the smaller ones serving outlying districts. The Atwater station serves southwestern Montreal and Verdun, districts where both industrial and residential consumption of power is heavy. The Mount Royal station serves the north-central section of the city. Somerled supplies the fast-growing northwestern residential district, while the Rockfield station distributes power to the heavy industry and homes of Lachine. O'Brien serves the rapidly expanding residential community of Saint Laurent and also takes some light manufacturing loads. The new and modern Delormier station in the southeast part of the city is an important link in the strategic network encircling Montreal. If needs be, any section in the network can be cut out completely and its load distributed among its neighbors. Like the waterfall which created it, high voltage electric power is difficult and dangerous to use. For instance, when you want to water your lawn, a waterfall is not much use. But once it is split into smaller currents, you can control it. You can even turn it off. You can do that with a waterfall and with electricity, once it's under control. The substation is the principal means of controlling incoming electric power. Its heart is the transformer. As the high voltage goes through the transformer, the power is split into smaller units, and in its new form, it begins the journey to our homes and factories. But before it enters our homes, the electric power must take another step down, through smaller and more familiar transformers mounted on poles here and there on our streets. In the same way, an even smaller version of the transformer is used by the youthful railroader to reduce household supply to the smaller force which drives his electric train. A low hum is the only sign that the transformer is at work. It operates as though by magic. No moving parts, no sparks, only the hum. But just what goes on inside the transformer? How does the magic work?
Well, I'll tell you. It's not very complicated, really, when you know how it's done. For instance, take this fella here. Of course, no one can see electricity, but if we could, the inner workings of the transformer would look fairly simple. There are not very many parts to it. All it consists of is a core with 2 or more coils wound around it. The core is made up of laminated steel, just sheets of metal shaped like square donuts, placed one next to the other. Around one side of the core is wound a wire carrying current at high voltage, say 120,000 volts. Let us imagine a number of little men representing the high voltage. As they race around the steel core, they create a magnetic field. We might say that each of them throws an arrow into the core as he goes by. Now, if another wire, a bigger one this time, is wound around the other side of the core, something else happens. The magnetic flux induces current into the low voltage windings. In other words, other little men pick up the arrows. But things are different now. The little men are bigger and there are not as many. And each one picks up not one, but several of the arrows. They move off, ready to shoot their arrows wherever electric current is needed, to light a lamp, to drive a motor, to heat a household appliance. What has happened is this. We had a power line at 120,000 volts pressure, carrying 100 units or amperes. We ran it through the transformer where it was picked up in a more convenient form. We took out the same force as we put in, but we have more pieces of the same power with which we started. We now have 1,000 units or amperes carried by 12,000 volts. Nothing gained, nothing lost.
The transformer does with electricity what a cashier does with money. The cashier converts bills into change. You give $1, you get $1. You get 10 dimes. You put in 120,000 volts, you get 120,000 volts. 10 times 12,000. Nothing gained, nothing lost. Because of the terrific force of the high voltage current received from the powerhouse, each piece of equipment in the substation must be on a very big scale. Electricity is rebellious stuff. It must be kept within bounds, as otherwise it would jump from the wires and streak down into the ground, destroying anything in its way. Big insulators act as fences for the power. When the power leaves the substation for distribution to its final outlets, it sometimes travels underground. Specially insulated cables carry the high voltage. Generally, they consist of a lead sheath covering conductors insulated by oil-impregnated paper. Each cable has its own conduit encased in concrete. Yes, everything must be big and strong and fast, like the circuit breakers, which are just like the light switches in our own homes. In our homes, a switch controls one or at most a few light bulbs. But a circuit breaker in a substation controls enough power to light up a fair-sized town. In less than 1/10 of a second, the power can be cut off. Automatic circuit breakers are of various types. Some of them operate in a sealed bath of insulating oil. There is other important equipment in the substation. Automatic voltage regulators, sensitive to every increase or decrease in the load, ensure a constant and exact flow of electric power. The control panel is the master of all the powerful equipment in the substation, the brain which directs the energy channeled through it. Everything looks very neat and pretty and well arranged and simple. But one look behind the front of the control panel shows just why it is the nerve center of the substation. There are literally tens of thousands of minute and delicate pieces fitted together with exquisite care to form a complex and sensitive instrument. There is no room for error here. Every detail must be perfect. Hourly readings make sure that everything about the station is running smoothly. Every one of the many instruments, gauges, and controls has a definite function. For instance, the ammeter shows a load of 200 amperes feeding the lights on the neighboring streets, while a special type of recording instrument will measure and record on a paper chart 16 different voltage readings once every 30 seconds. The relay is a miracle of compact engineering design. In a split second, it can tell exactly where a fault or break has occurred in the distribution lines. In a growing metropolis such as Montreal, there is a constant need for additional power, a demand created by the development of new housing projects and the expansion of new industries in outlying districts. Since each substation can only serve an area of about 2 miles square, new ones must be built to keep the wheels of industry turning and to serve the needs of the individual householder. Electricity is vital to the well-being of modern Canadians. The demand for power grows at an ever-increasing rate. Careful planning must be done for years ahead, for houses and factories as yet unbuilt. In the drafting rooms, engineers are working on power plants, lines, and substations which do not yet exist, working for tomorrow so that no matter how the city grows, there shall be power ready before demand. Every one of the many steps involved in construction must be carefully planned. Each one of the tens of thousands of pieces of equipment, whether large or small, which go to make up the substation, must be designed in fine detail. Powerful modern equipment goes to work to level the site chosen for the new station. Great shovels dig to a solid footing to support the structures. Concrete is poured. The foundations must be good, for the equipment is heavy and must remain absolutely level and steady. The steel framework of the yard is erected, the beams and girders that will support the heavy electrical equipment. The welders, the carpenters, the plumbers, and pipe fitters do their respective tasks, and soon the building begins to take shape. The heavy equipment begins to arrive from the electrical manufacturing plants all across Canada. A giant transformer weighing more than 60 tons was manufactured hundreds of miles away. It is moved into position gently and with a delicate care accorded a fine watch mechanism. There are myriads of small parts, connectors, relays, switches, nuts, and bolts. Each one of these had to be designed, ordered, manufactured, and delivered to the site before being installed. Electrical crews fix up the circuit breakers, wire the complicated control panel, and make ready the other equipment. Gangs of linemen string the transmission lines which feed the substation from the powerhouse and link it with the network. At last, the job is done. Everything is ready to turn on the juice, to bring in the electric power. The new substation has taken its place in the extensive network established throughout Greater Montreal. A diagram in the central control room shows all the substations and their interconnections in the network. The system supervisor knows what happens in each of them. An open circuit breaker, a dead transmission line, everything of interest is reported immediately to the supervisor, who directs whatever action may be necessary. Despite all the protective equipment, the age-old enemies of man, wind and lightning, can still interrupt the current by breaking the line. But when trouble strikes, the substation is ready. The line break is revealed immediately by an automatic signal, and the emergency department swings into its efficient routine.
Supervisor.
Beaumont 17 opened on short, 218.
Beaumont number 17 opened on short at 218. Will you test it, please?
Okay, hold the line. Short still on, 219.
Number 17 tested and reopened automatically. All right, leave it out until you hear from me. Service. Yes. Beaumont 17 open on a short and tested dead short. Okay, Jack. I'll send a patrol right away on it. Thank you.
CY5Y calling car 306, calling car 306, come in car 306.
.306 to CY5Y.
CY5 with a car 306. Beaumont 17 open on a short and tested dead short. Go to the cable pole on curbs, east side, north of Beaumont, and open the switches and call me back.
Beaumont 17 open on short. You want me to go to the corner of curbs, west of Beaumont, and open the switches of the cable head?
That is correct.
Okay, we'll go there right away. 306 off of CY5Y.
The operator in the emergency room is but another link in the guardian system which ensures the steady stream of power to the 2 million people served by Hydro Quebec, a system which is built on the keystone of power substations. Listen to the great transformers. Listen to their hum. Deeply they sing of man's victory over the powers of nature, the harnessing of that great force which is electricity. And in the last analysis, the victory is won mainly by the workaday substation, the symbol of man's real victory.